All right, so let's scoot on to a new topic. We're talking about algebraic limits and continuity. Now, in a different lecture, we actually spoke about algebraic limits. In this section, we're going to formalize it first off with a theorem. And we kind of use this theorem common sense-wise without it formally being stated until now. But let's look at this theorem. It is called the limits of rational functions, and it says for any rational function f with a in the domain of f. So since a is in the domain of f, when we graph, it would represent an x value, wouldn't it? Okay, so look at the way they've written the limit. The limit as x approaches a of f of x equals f of a. How did they get f of a? What did they do to get the f of a? Yes, they took this number that x is approaching and they were able to plug it into that x. Good? Okay. Let's look at this first example. They're asking us to take the limit as x approaches 2 of 4x minus 5. So, based upon this theorem, how are we going to find the limit of this? Yeah, very good. What we're basically going to do is we are going to take that number, that x approaching the 2, and substitute it in for the x, which in this case will give us 3. Which tells me the limit as x approaches 2 of this function 4x minus 5 is equal to 3. Good? Okay, let's look at this one. Again, we're looking at its algebraic limit, and we're looking as x approaches 3. So for us to figure it out, what are we going to have to do? Good, we're going to have to plug the 3 in for the x, right? Okay, so I'm just going to do some work down here. And by the way, it's nice that we're actually able to plug the number in, like we did in a previous lecture. Sometimes we're not able to plug that number in, so we can't look at it algebraically. We would have to look at it graphically, all right? But for now, we're looking at it algebraically. So let's see what we get when we figure this out. What do we get in the numerator? Good, 1. And the denominator? 1, which means we get the limit equal to 1. Good? Cool. Hang in there. Got a few more examples for us. All right, so let's look at this next example, number 3 up here. Now, remember, the theorem's title was the limit of rational functions. Rational means, good, a fraction. So we could be talking about us taking the limits of functions that are fractions. Hence number 3. Now, if you take a look at number 3, we're looking at x as it approaches the number 3. Now, I'm seeing a little bit of a challenge. I'm not sure if you are or not, but I'm noticing that denominator, and I'm noticing that if I plug in the 3 in the denominator goes to 0, which means it's undefined, right? And you're like, well, that means there's no limit. Well, it means that the limit doesn't exist, right? However, I'm noticing the numerator is x squared minus 9. And what can we do with that numerator that might help us out? Good, some of you said it, we could factor it. So, I'm going to do some side work over here, and I am going to take this x squared minus 9, and I'm going to factor it. So yes, I'm assuming you remember how to factor. Alright, so when we factor, this is what we get. Notice those x minus 3's cancel, don't they? Which means in actuality, I am taking the limit as x approaches 3 of x plus 3. That's what I'm actually taking the limit of, because the x minus 3's canceled out. With me? Okay, well, if I take the limit as x approaches 3 of x plus 3, what do we get? Good, we get 6. Awesome. Good? Yeah, it's helpful that when we look at a rational function, it's helpful if it factors, because it actually will take care of the challenge of us finding the limit, as in that denominator of x minus 3. Cool? Okay, so let's look at this fourth example. And again, I'm taking the limit of this rational function, but I'm seeing a challenge. Are you? Yeah, this denominator, if I plug in that 1, goes to 0 again, doesn't it? Okay, well, what do you think we should do to help us out? Good, factor. So again, I'm assuming you remember how to factor, and if you don't, go look in a previous lecture. So the numerator, I'll give you a few moments to factor it. Okay, did you get it? All right, let's see if we agree. I got this. Do you agree with me for the numerator? Excellent. And then the denominator also factors in this case, doesn't it? Good. Do you see what will happen? Yeah, those x minus 1's drop out, don't they? Which actually leaves us taking the limit, and I'm going to put it here, the limit as x approaches 1 of the rational function x plus 6 over x plus 1. No problem to plug that number in, is it? Okay, so when we take this limit, what do we get? Excellent, we get 7 over 2. With me? Agreed? Okay. Number 5. Another rational function. Kind of getting the idea of what you probably got to do here? Yeah, you're going to have to factor. So, pause the video, go factor it, and then come back and let's see if the two of us agree. Shall we? All right. I am getting in the numerator for my factoring. And in the denominator, I am getting this. And the x minus 2's drop out, don't they? Yay! All right. Let's look at what we're still taking the limit of then. We are taking the limit as x approaches 2 of the rational function x plus 5 over x minus 2. Well, that's a nicer rational function, isn't it? But what happens when you plug that 2 in? Yeah, the numerator is a 7, but what's the denominator? Yeah, that denominator is going to be a 0. You end up with 7 over 0, which is undefined. Is that a viable answer, undefined? Nope, you're right, it's not. So let me ask you something. What do you think is going to be the limit of this rational function as x approaches 2? Good. I heard some of you. In this particular case, it does not exist. Cool? With me? Yeah. You're like, I know. The factoring should have taken care of it, but it didn't. So be it. All right? All right. Number 6. Yeah, you plug that 25 into the denominator, it goes to 0, doesn't it? And you're like, yeah, but how do you, can you factor that? Actually, you can factor it. And most of us have never factored that, so you're like, well, how do I do that? Okay, just watch. Don't write, just watch. What I need you to remember is how you can write the square root of x as another way with an exponent. X to the what? Remember, this is the square root. That's an x to the first power. Good. X to the 1/2, which means the numerator can be rewritten as x to the 1/2 minus 5 over x to the first minus 25. With me? Again, don't write, just watch. Now, here's where I'm going to direct us to. I'm going to direct us over here to where we factor the x squared minus 9. And I know it's x plus 3, x minus 3. The plus 3 and the minus 3 is not the issue, right? This x and this x, they're both to the power of 1, aren't they? Because 1 plus 1 equals the 2, doesn't it? Remember, when you multiply those x's, you add the exponents, don't you? So the x to the first times the x to the first basically means it's x to the 1 plus 1, which is x squared, which is this x squared in the front. Agreed? Okay. I'm going to apply that same principle to the x to the first minus 25. I'm going to leave the numerator alone, it's going to stay x to the 1/2 minus 5. Now the denominator, if we factor it, we know we could put a plus 5 and a minus 5 to get the minus 25, yes? But the question is, what do these x's have to be? Because notice, this is a perfect square, just like the 9 was a perfect square. And the x to the second is obvious, it's a perfect square. X to the first, most people wouldn't think of as a perfect square, but in actuality it is. This is still a difference of squares, just like the x squared minus 9. The catch is, you've got to think outside the box, and you've got to go, well, if the 2 breaks down to 1 and 1, then the 1 is going to break down to what plus what? Remember, it's got to be 2 the exact same. Good, I think I heard some of you. 1/2 and 1/2. Because 1/2 plus 1/2 is 1, isn't it? Yeah. This one was not obvious to factor, but it is, the denominator still perfect squares, even though that x to the first didn't look like it. Okay, gratefully recognizing that, now we can cancel these two out, can't we? My recommendation is you pause the video, go back to the beginning of number 6 and how we factored this, and then play it forward again and catch up if you still need a little bit, or you still need to hear the explanation again. Cool? Okay, in the meantime, these two guys are going to cancel, which is going to leave me 1 over x to the 1/2 plus 5. Cool? Okay. Which means we are taking the limit as x approaches 25 of 1 over, now the square root, or x to the 1/2 can be written as the square root of x. So I'm just going to write the square root of x plus 5. Which means when I plug in that 25, I'm going to get 1 over the square root of 25 plus 5, which, yeah, 1 over 10. Because the square root of 25 is 5, isn't it? That makes sense? Yeah, number 6 was a little oddball-y. Why? Because you had to factor something you're like, I've never factored that before. Didn't know we could factor it. We can factor it, all right. Cool? Okay, hang in there, because we're going to be talking about some properties of these limits. I'll be right back. All right, so let's start looking at the properties of limits. First off, we are reading that if the limit as x approaches a of the function f of x is equal to L, and the limit as x approaches a of g of x is equal to m, and then I have this c, and c is a constant, any constant, then we have these particular properties. So now, the first property says you're taking the limit as x approaches a of c. What did c represent again? It was a constant. Do you see an x here? Yeah, neither do I. So remember the examples we just worked with. If there's no x there, can you plug an x in? No, you can't. You can't plug in anything. So what do you think the limit of a constant would be? Yeah, it would just be the constant. It would just be c. Good? Okay. Now, I'm taking the limit as x approaches a of the function f of x. But now f of x has a power. It has an exponent. So here's the deal. I could take this function and I could raise it to the k power. Now, I'm going to kind of remind you of something that we did. Remember we took the limit of whatever x approached of the 4x minus 5. What happens if this was to the power of 6? Do you really want to take this 4x minus 5 to the power of 6 and then find the limit and then plug in, what was it, 2? Let's just say it was 2. Do you really want to do that? Or might it be easier to plug the 2 into here first, find that answer, and then take it to the power of 6? Yeah, it would be easier to do it the other way around, wouldn't it? So, in this particular case, I can actually find the limit as x approaches a of the f of x first. Once I have that answer, then I can raise it to the power of k. And based upon what is written up here, the limit is L, which means L would end up being to the power of k. Cool? Yeah, this example really kind of brings it to home. You're like, oh yeah, I don't want to multiply this out 6 times and then plug the 2 in. I'd rather plug the 2 in first and then multiply it out 6 times, right? Okay. Now there's a couple of restrictions here. First restriction is this. Your k is a power, right? It's an exponent. The k has got to be an integer. Remember, sometimes it's easier to describe what's not an integer. An integer is not a fraction and it's not a decimal. Good? Okay. The other restriction is this, and it's on the L. And it is stated that if k is negative, remember, if you have a negative exponent, that means this thing goes to the bottom, doesn't it? So if k is negative, your limit can't be equal to 0, because if your limit's equal to 0, then it's undefined if you have to drop it to the bottom. Cool? Okay. Let's look at number 3. Number 3 kind of go hand in hand with number 2. Just imagine if instead of the power of 6 here, just imagine if this was asking you to take the 6th root of that. You're like, how do you take that? That's exactly my point. How do you take the 6th root of 4x minus 5? But if I could plug the 2 in first and then take the 6th root, easy peasy, right? Okay, so same scenario. We're going to take the limit first as x approaches a of the function. And then, once I have that answer, I'll take the nth root. And again, that limit was L. So I'm going to take the nth root of L. Cool? All right. Now, 2 restrictions again. First off, n is the index of the root. So first off, n has to be greater than or equal to 2. So a square root or higher, right? I mean, the first root of a number, we don't take first roots of numbers, so n has to be 2 or higher. The second restriction is if n is even, right? You can only take an even root of a positive number, right? I can take the square root of 16, but I can't take the square root of negative 16 and still be in our real world, right? I can take the 4th root of 16, but I can't take the 4th root of a negative 16, right? Okay. I can take the cubed root of a negative number, but not the square root of 4th root, right? Okay, so if n is an even number, then L, whoops, there's a then, I need an n there, then L must be greater than or equal to 0. Good? Does that make sense? Okay. Hang in there. I got 4 more properties to talk about. I'll be right back. Okay, so let's look at the last 4 properties. In property number 4, the limit as x approaches a of, first I have to add these 2 functions together or subtract them. That's what it's saying to do first. Once I add or subtract the 2 functions, then I'm supposed to take the limit. Well, depending upon the functions, it could be easy to add them and subtract them, or maybe it's not so easy to add or subtract them. The nice thing about this property is it will allow me to actually take the limit of f of x and then take the limit of g of x, both of them as x approaches a, and then add or subtract them together. Which means I would be adding or subtracting their limits together. Cool? Okay. Property number 5 is kind of along the same lines as property 4. First thing it's asking me to do, since these are in brackets, is to actually multiply the two functions together. Well, if you've got a third degree function and even a second degree function, you know, sometimes you just don't want to multiply those together first. Sometimes it's just a pain to do that, right? And if you just miss one little thing, it could mess it all up. Gratefully, we would be allowed to take the limit as x approaches a of f of x, and then once I get that answer, I could multiply it by the limit as x approaches a of g of x, which basically means I'm multiplying the two limits together. Good? Makes sense? Okay. Let's look at property 6. In this case, we're dividing. Kind of get the idea of what we could probably do with property number 6 based upon what we are able to do with properties 4 and 5? Yeah, good. I could actually take the limit of the numerator and then divide it by the limit of the denominator. That'll be a whole lot simpler, because sometimes you can't even divide the polynomials. So what are you supposed to do if you can't even divide it? And then you would basically take the L divided by M, right? Because those are the limits of each one. But this one has a restriction, right? If it's L over M, what can you tell me about M? Yeah, M can't be equal to 0. If M is equal to 0, it's undefined and there's no limit there. Cool? Okay. This property 7, the last one. Notice it's asking me to take the limit of a constant multiplied by the function. Well, remember property number 1? What's the limit of a constant? Yeah, the limit of a constant is just a constant, isn't it? So here's the deal. This one we can write as the limit as x approaches a of c multiplied by the limit as x approaches a of f of x. I'm using property number 5, aren't I? I can actually take the limit of each of these individually based upon property 5. Agreed? Okay, but remember what we said. What's the limit of a constant? Yeah, the limit of a constant is just the constant. And then we'll have the limit as x approaches a of f of x, right? Well, in this case, it'd be just c times L. Good? Okay. So stay tuned. I actually have some true or false problems for you to see if you understand these properties. I'll be right back. All right, so let's take a look. We've got 3 true or false statements, and they're based upon the properties we just spoke about. So let's look at the first one. The first one says, the limit as x approaches 3 of 7 is equal to 3. Don't answer. First off, you've got to stop and think. You're like, what would that be? So here's my recommendation. My recommendation is this. Look at the problem, but erase the answer. With me? Look at the problem, but erase the answer. They're asking me to take the limit as x approaches 3 of the number 7. Do you see an x with that 7? Neither do I. So if there's no x with that 7, can I plug that 3 in? No, you're right, I can't. Which means in this particular case, 7 is a constant. Which means in this particular case, your answer should be what? 7. Because, right? The limit of a constant is a constant. But what did they have? Yeah, they didn't have a 7. They had a 3. But we were supposed to get a 7. So is this a true statement? Nope, this was a false statement. The limit as x approaches 3 of 7, they said was 3. That's a false statement. Our answer should have been 7, not 3. That's why it's a false statement. With me? What property was that? Yeah, that was the first property. Cool? Okay. And by the way, you don't have to remember the property numbers. I'm just trying to lead you back to them so you can take a look if you need to. Okay, so let's look at the second one. If the limit as x approaches 2 of the function is 9, then the limit as x approaches 2 of the square root of the function is 3. Again, don't answer. Don't say true or false. Don't answer because you've got to prove it. You've got to prove whether it's true or you've got to prove whether it's false. Are you with me? Okay, so let's start off here. They said the limit as x approaches 2 of f of x, right? We know that's 9. Agreed? All right. This says take the square root of it. Okay. Now help me out. Based upon one of the properties that we spoke about, if they're asking me to take the limit of the square root of a function, do I have to do the square root first? You're right, I don't. And you're like, wait, which property is that? I believe it's property 3. Go back and take a look. Do you have to take the square root first? No, you don't. You could literally take the limit of the function and then take its square root according to that property. Cool? Okay, now we know the limit as x approaches 2 of f of x. It was here in the if part. It was a 9, wasn't it? So they're literally asking me to take the square root of 9, aren't they? Is that equal to 3? Yes, it is. So is this statement true or false? Yep, this is a true statement. Cool? This is the work that proves it. You've got to prove it. You just can't guess yes or no. You've got to prove it. You got to go, well, which property can I utilize? Cool? All right, go to number 3 here. They're saying if the limit as x approaches 1 of the function is 5, then, whoops, I think I forgot to write something. Okay. Again, before we say true or false, let's go back and write this. The limit as x approaches 2 of g of x, right? But they're saying take the function and square it. Well, help me out. Based upon one of those properties, do I have to actually take the power first? You're right, I don't. Based on one of those properties, and I think that's property number 2, I could literally take the limit first, and then I could square it. Couldn't I? So in this particular case, the limit as x approaches 2 of g of x, yeah, that was 5. So I would get the answer of 5, and then I could square it. And yeah, we get 25. So is this statement true or false? Yep, this statement was also true. Does that make sense? Okay, hang in there. Got a couple more examples. Okay, so I decided to skip those couple of examples. Why? Because they're like the last 3 we just spoke about. I decided instead to move on to a definition of a continuous function. So we're going to come across functions, be they algebraic or an actual graph, and we'll need to decide if those graphs or those functions actually represent a continuous or a discontinuous function. So let's look at the definition. This is a definition of continuous. And it reads, a function f is continuous at x equals a. So again, a is a value of x, which means that's the domain. If, notice there's 3 requirements that need to be met. For this function to be continuous, all 3 of these need to be met. Got it? Okay. The first requirement is f of a must exist. So when you plug the a in for the x, it exists. The second part, or the second requirement, is when you take the limit as x approaches a of f of x, it exists also. So not only does f of a have to exist, but the limit of the function as x approaches a must also exist. And then the third part is very crucial. These 2 may exist, and that's great, but the third requirement is this. These 2, parts A and B, must be equal to each other. They've got to be equal to each other. If f of a exists and the limit exists, they better equal each other. They better be the exact same point. Because if this one exists and this one exists and they don't meet, then it's not continuous. Are you with me? Okay. So all three of these must be met. Now, a function is continuous over an interval I if it is continuous at each point A in that interval I. So if you've got an interval, let's say from 1 to 3, then every number in that interval, this needs to be met. Got it? If you want it to be continuous over that interval, then all three of these requirements need to be met. If f is not continuous at x equals a, we say that f is discontinuous, or it has a discontinuity at x equals a. Cool? Okay, so hang in there. I've got some examples for us.
Okay, so let's take a look at this particular graph. And we're going over continuous and discontinuous functions. So this is asking whether this function is continuous over the interval from -6 to +6. Now, when you look at this particular interval, it is representing the x's. So as I travel from -6 to +6 on the x's, I am looking to see if this function is continuous. Now, a very simple way to decide if a function is continuous is to take your pen, start drawing on this graph, and if I have to pick my pen up to continue the graph, it is discontinuous. Notice that break right there. Notice the dotted line here at x being equal to 3. That tells me that it splits the graph into two pieces. So this is definitely not a continuous function. Does that make sense? Okay, let's scoot on to the next one. We're taking a look at this graph. It is called k of x, and it is giving me 3 questions to answer. So let's look at part A. It wants us to find the limit of this particular function as x approaches 0. Well, remember, I have to come in from the left and from the right. So as I come in from the left and I follow this graph along, I notice that it is approaching this point. As I come in from the right and approaching 0 on the x's, it's approaching that same point. So remember, your output for the limit, is it an x value or a y value? Good, it's a y value. This particular point that we're approaching is 0, -1. So in this particular case, our limit as x approaches 0 would be -1. There's part A. Let's look at part B. Part B is asking us to literally find k of 0. Well, that means for part B that they literally want k equaling 0. Or pardon me, I shouldn't say k equaling 0. I should say that they literally are looking for where x equals 0. Well, where x equals 0 is actually an open circle. And since this is an open circle here, then there is no y value that goes along with k of 0, which means in this particular case, for part B, the function is undefined. So for k of 0, your function is going to be undefined. Good? Okay, now part C wants to know if this function is actually considered continuous. Well, remember the definition that we went over a few minutes ago. We need to have the limit exist. Well, the limit exists in part A. We also have to have that when you plug in that x value, that we actually get an answer. It actually exists. Well, part B doesn't exist. It's considered undefined. Why? Because I have an open circle. When x is 0, it approaches -1 for the y's, but it never is actually equal to -1 on the y's because there's an open circle there. So in this particular case for part C, the question is is k continuous at x equals 0? And this answer is a no. Does that make sense? Part B failed us. Since part B failed, then part C is no on that. And by the way, if you take your pen and you're drawing along on this graph and all of a sudden you hit that hole, you've got to make a jump to continue. That's also kind of a visual look-see if this thing is considered continuous or not. Cool? All right, let's look at one more. And we are using this graph once again to decide if, to answer these 4 questions and eventually decide if this is continuous or not at the particular number. So, part A wants us to find the limit of that function as x approaches 4. Notice this plus sign from the right. So, as we come in from the right, this is the graph we're going for. And as I approach x equals 4, which is right here, it looks like this is approaching what number? 1, 2, 3, 4. It looks like it's approaching 5. So let me try that again. It looks like it's approaching a 5. So, and then the second part of part A is asking us to find the limit as x approaches 4, but from the left. So as we come in from the left, I am going to be on this line right here. And as I approach that 4, it looks like it's going to be a 1 for that y. So the limit, and I'm going to write it off to the side here, the limit as x approaches 4 from the left of the function looks like it's actually equal to 1. So from the right, it approaches 5, and from the left, it looks like it's going to be a 1. So notice part B. Part B then is asking us to find the limit of the function as x actually approaches 4. Well, if from the left and the right is approaching 2 different numbers, do we have a limit? Good, you remember from a previous lecture, we don't have a limit. So on part B, the limit does not exist. Does that make sense? Your limit does not exist for part B. Good? Okay, let's look at part C. Part C is actually asking me to find f of 4. In other words, when x is equal to 4, what is y equal to? Well, if you notice at the 4 here, I have got this dot and I've got this dot. Now, do I look at both of them or only one of them? Good, you're only going to look at one of them. You're only going to look at the solid dot because the solid dot is where x actually is equaling 4. And that solid dot is the point 4, 1. So when x equals 4, y is equal to 1, which means in this particular case, f of 4 would equal 1. Good? Does that make sense? Okay. And now there's a part D. And part D is saying, well, finally, they are asking the question, is this function continuous at x equals 4? Well, remember the definition. If it's going to be continuous at x equaling 4, that means that the limit as x approaches 4 has to exist, and when you literally plug in the 4, I actually have a physical answer for the y. Well, part B, does my limit exist? No, that's where it's going to fail us. Part C, this one actually exists. I do actually have a y value that is associated with x equals 4. So part C is good. Part B is the one that fails us. The limit does not exist. So part D, is it continuous? No, it is discontinuous. Why? Because the limit as x approaches 4 of the function does not equal f of 4. Cool? Okay, so hopefully this section makes sense to you now that we've done a few examples as well, graphically speaking. You guys have fun with this stuff, and I'll catch you on the flip side.